So hello and welcome to lecture number 6, I believe. No promises on that, but I'm pretty sure it's 6. The mathematics of counting. What we mean by counting is figuring out formulas to count the number of ways something can occur without doing it by brute force. So by brute force, I can list all the possible ways something can occur, but that could take a really, really long time. So instead, we try to come up with formulas to do it for us. And on the PowerPoint, the very first formula is called the fundamental principle of counting. The fundamental principle of counting is based on the concept of multiplication, and as such, can be taught alongside the 3rd grade standard of represent and solve problems involving multiplication. So this is a 3rd grade and above concept, the fundamental principle of counting. Let's demonstrate it by the next slide. Example. It says, Pat has 4 shirts and 3 pairs of pants. How many different ways can Pat pick a shirt and a pair of pants to wear?
Oh, I think I remember these problems.
You know Pat? Oh, okay. Okay.
No, I just remember these problems. Sorry.
I understand. No, don't have to apologize. I personally do not know Pat, and I'm really confused about who he or she is. But nevertheless, the question is, how many different ways can Pat pick a shirt and a pair of pants to wear? So there's 2 ways to make a picture to help us answer this question. The first way is called the area model. And the area model, as you can see there on the next slide, on slide number 3, wherever we are. The area model is to list one of the 2 possibilities vertically, pants or shirts. In this case, they do shirts vertically, and they do pants horizontally. And as you can see, there are 3 pairs of pants, blue, black, and white. 4 shirts, red, blue, green, and black. And notice that what we create here is a little grid. And what you should see about that grid is that every one of the overlapping squares or rectangles is the same size as all the other ones, correct? Which is our indication of what? What do you think psychologically the same size rectangles corresponds to?
Same probability.
What part of probability? Same size rectangles corresponds to what concept?
All possible outcomes?
Not all possible, because even if they weren't the same size, they might be all possible outcomes. What is the same size part telling us?
That they're equally likely?
Yes, that they're equally likely outcomes. Yeah, raise the roof, sister. There we go. That's what I'm talking about. Boop, boop, boop. Yeah, so equally likely outcomes. That's the idea of the same size squares or rectangles. So psychologically, we imagine equally likely. And how many rectangles are we counting as we look through this grid?
12.
12, which tells us that we have 12 possible outcomes for Pat wearing shirts and pants, correct? Yes?
Yep.
Yes.
Seems very reasonable, correct?
Yes.
Okay, so now the question is there a way I could have gotten that result without drawing the area model? And the answer is, well, there's 4 ways for one outcome, 3 ways for the other outcome, and somehow the answer is 12. So exactly what rule would apply to take a 4 and a 3 and get a 12? Multiplication. And this is the fundamental principle of counting, that if there's a certain number of ways of having one outcome, and then a certain number of ways of having a second outcome, if I want to calculate how many possible ways there are altogether, I multiply, which goes back to my question earlier. How many different outcomes are there when you roll 2 dice? So Talar, you said 12 because you multiplied 6 times 2. But the first outcome has 6 ways. The second outcome has 6 ways. So therefore, the total number of outcomes is 6 times 6, or
So
36 outcomes. So if we go back to my question, which is how many ways could there be, if you roll 10 dice, how many outcomes are there? Then what would the answer be? I'm not looking for an actual number, but more of an expression. Tell me how to get it. How would I get the number of outcomes for 10? You got a calculator? What does the calculator say?
60,466,176 ways.
Yeah, I was way off.
You think?
Just a little.
I was thinking it would be a lot bigger than that, but you're right. It's only 6 million something, right? 60 million something. Only 60 million something.
Oh my.
Yeah, so you said 660 million. Hey, they both start with the number 6. They can't be that far off.
Hey, I tried.
That's all you can ask, right? That's all you can ask. Okay. So this is the fundamental principle of counting, which says that you multiply. Now we'll get to that on the next page, but for now, let's answer this question. If Pat picks clothes at random, what is the probability that Pat's pants and shirts are the same color? Now, we are also assuming here that Pat knows nothing about fashion and that any combination of colors is perfectly acceptable. So Pat is like me in that sense. Okay, so the question is, what is the probability that
2 out of 12?
2 out of 12? That's right, 2 out of 12. Yeah, that's wonderful. Look what Soler did. She actually used colors to make like those little dots, and then just saw which squares or rectangles have the same colors. I think that's wonderful. Or you can just see that you can have black and black, you can have blue and blue, but since there's no black and black, blue and blue, but there's no red and green pants, there's no white shirts. So the only way is those 2 out of 12, there's your answer. Seems reasonable, correct?
Mm-hmm.
So that is the area model. The next slide gives you a different model, which is called a tree diagram. This is not a new question. It's the same question and has a different approach to the answer. A tree diagram is used when you have a sequence of steps. Those steps could be picking a pair of pants, picking a shirt, or vice versa. It could be rolling the first die, rolling the second die. It's any situation where the events are sequential. That one thing occurs and then another, and then another, and then another, and so on. In this case, what is the first step of the tree diagram? Picking a 1. What is a
Shirt?
picking a shirt, right? The first set of branches, I don't know what you want to call it, but the first column of actual information in the tree diagram are the various shirts that you could wear. What are the various shirts that you can wear? Well, it can be red, blue, green, or black, correct?
Mm-hmm.
Now, once you've chosen a red shirt or a blue shirt or a green shirt or a black shirt, now we go to the next step of the sequence, which is pairs of pants. Notice how we have 3 lines coming out of every shirt because every pair of pants is possible with every shirt.
Mm-hmm.
If you instead said, well, I know something about fashion and I can never wear a blue pair of pants with a red shirt, then it's possible that your second set of branches might not be the same amount in each one. There might be reasons why you would remove one. And it wouldn't be 12, it might be something else. But that's a more complicated question. Talar, go ahead.
So say if we don't like tree diagrams, would we be able to use the area model interchangeably?
Well,
Or would it have to be one or the other?
so you certainly can in this problem, but we're going to see in a few minutes a situation where only one of them is appropriate, and we'll try to understand why. I don't want to give it away because I'm not really into spoilers, but you know, just saying he was dead the entire movie, just putting it out there. But what we're going to do is we're going to see a situation where one is good but not the other.
Okay.
Okay. All right. So let's go to the next slide. It says the Honda Civic LX the Honda Civic LX comes in 2 interior colors and 8 exterior colors. First, before we even do anything else, 2 interior, 8 exterior, how many combinations are there?
16.
16, right? 2 times 8. 2 events in succession, picking the interior, picking the exterior, or vice versa. No problem, Namira. Good that you're here, but stay after class for a minute. I want to speak to you if that's okay. It won't take long, I promise. You're not in trouble. So there's 16. So let's do this via a area diagram. And let's also do this via a tree diagram. So the first question is, if we were to do an area diagram here, does it make a difference which one's vertical and which one's horizontal?
No.
No.
Well, usually not, but there's a certain amount of space that was given to make your little picture here, correct?
Yeah.
So
Yeah.
certainly one of them is better for this particular page.
The interior color being the let me mix this up. Vertical?
Yes, the interior color being vertical because there's a lot of space to put 8 things side by side.
Yeah.
And not so much space to do it that way. So yes, you're right in general, it makes no difference. But I think here, 2 up, down, 8 left, right is certainly a more appropriate usage of the space. Would you agree with that?
Yeah.
But it really doesn't matter.
It really doesn't matter. If you write really small and you can fit it in, knock yourself out.
Okay.
I mean, not literally, you know, that would be hard, but you know what I'm saying. I don't even understand the expression, knock yourself out. What does that even, you know what, whatever. Let's just keep going. So, and then after you do that, and hopefully it's relatively straightforward how to do that. And so Lara, if you have all the colors, that's wonderful. Those colors, when I look at them, are pretty redundant. Like I wouldn't even know how to differentiate some of those colors. I mean, obviously red, blue, and black I get, but and white. But like there's gray, another
There's
gray.
gunmetal.
There's metallic gray, there's lunar gray, there's cloud gray.
One of them has to be silver.
Yeah.
So the friendly school version of 50 Shades of Grey, also known as the Honda Civic.
Yes, that's the PG rated version.
Yeah.
Exactly. So yeah, I had a car. My last car years and years ago was a Jeep Grand Cherokee back when they were still in style. You don't really see them anymore, but
Those things are cool.
they are cool. I know. I went from a Jeep Grand Cherokee to a Prius, so that's like a full 180. It's like let's just waste gas to let's not use any gas. It's crazy. But anyways, my car was taupe. That was the color, taupe. And I'm pretty sure one of those looks like taupe. I just don't know which one it is. Anyway. But
yeah, they all look the same.
they all look the same. So I would, instead of labeling like my colors, other than red, blue, and black and white, I might label the other ones like just A, B, C, D. I don't know.
All right.
I mean, do
Did
what you
it with
want.
numbers.
Yes, exactly.
Numbers.
Even better. Oh, look at that. Damn girl. Crazy.
You're smart. You're ahead of us.
Crazy. Of course,
I thought the visual might help.
right. The only problem with that, though, is that you have nowhere in your diagram where you're indicating what each number represents.
Yeah, but then, I mean, that's too much.
Oh yeah. We don't do
Yes,
that.
bossy.
Yeah, sure. Yeah. Right. So, okay. Where was I? Okay. So that was an area diagram, and then it says construct 2 different tree diagrams. 2 different tree diagrams to illustrate the same situation of different combinations. So just in theory, without actually doing it, I mean, you can do it if you want, but just in general, what do you think they mean by construct 2 different tree diagrams for the same situation?
So one would have like the first, I don't know what you'd call it, column would be the interior, and then with each exterior, and then the second tree diagram would be the first column being the exterior with the 2 interiors.
That's exactly it. All right, that's exactly it. Interior than exterior, or exterior than interior. Does one have more branches overall than the other? Would
No.
one would no, because if you do two, then if you do two and each of those two has 8,
Mm-hmm.
or if you do 8 and each of those 8 has 2, it's still going to be 16 branches overall. Yes.
Is it? Because I think the second one I drew has more branches.
Really? Let's see them.
So I counted 16 right here, and then
Yeah.
there's another 8 here when you start.
Oh, okay. So there's 2 for each of the 8 plus the original 8. You're right. You're right.
Right.
You're right.
Okay.
You are correct. So if you do it by saving ink or saving lead in your pencil, then yes, it does make a difference. Even though the number of endings will always be 16. But you are correct. That depending how you do it, changes how much work you're willing to put into the problem. And while these particular problems are relatively straightforward, it can get more complicated. And in that case, you might actually want to take a few minutes and say, okay, how can I do this with the least amount of work? Which is, after all, what everyone should always aspire to, right? How do you accomplish your job with the least amount of work possible? That's the goal in life. Okay, so all of this is summarized on the next slide by the fundamental principle of counting. If there are A ways to do one thing and B ways to do a second, then there are A times B ways to do both of them. Does that make sense?
Mm-hmm.
And that's shouldn't be really shocking based upon what we've done so far. Right? Based upon what we've done so far, that should be relatively straightforward. And if there are C ways to do a third thing, right? If there are C ways to do a third thing, then there are A times B times C ways to do all 3.
Mm-hmm.
Make sense? And so on.
Yes.
And so on. What does the and so on mean? If there's 4 things, it's A, B, C, D. If there's 5 things, it's A, B, C, D, E, and so on. Okay? So it says, use the fundamental principle of counting to count the number of ways a sequence of 5 flips can turn out. I assume they mean 5 flips of a coin here. It didn't say, it could be flips of a person. I don't know.
So it would be 10. So 5 times 2.
No, it's not 5 times 2. You are violating the fundamental principle of counting, which
Okay.
says, first flip, how many outcomes?
1 out of 2. 2.
2. Second
24.
flip, wait, second flip, how many outcomes?
2.
2. Third flip, how many outcomes?
2 again.
Fourth flip, how many outcomes?
2.
Fifth flip, how many outcomes?
2.
2.
And what does the fundamental principle of counting say? If you have a sequence of events,
2.
you multiply 2 times 2 times 2 times 2 times 2.
So it
Which is-
technically would be 2 to the 5th.
Or which is 2 to the 5th, which becomes
Makes sense.
32.
32.
Yeah.
32 possible ways of having 5 of possible outcomes after 5 flips of a coin. Right?
Do you
Choose the
mind
flip
going
flop.
over that again? I didn't really get that.
Sure. So you have 5 flips, correct?
Yes.
So there's a sequence of 5 events. Flip number 1, flip number 2, flip 3, flip 4, flip 5. How many outcomes are possible for flip 1?
2.
2. How many outcomes are possible for flip number 2?
That's what I don't get.
Just the second flip. Ignore everything else. You're flipping a coin. How many outcomes?
4.
Just the second flip. How many outcomes?
Oh,
2.
2. Just the third flip. How many outcomes?
2.
Just the fourth flip. How many outcomes?
2.
2.
Just the fifth flip. How many outcomes?
2.
Multiply, 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 multiply. What do you get?
Okay, 2. 32.
32.
You.
Does that make sense?
Yes.
This is the fundamental principle of counting. It says you multiply the outcomes, and that gives you the total number of ways. Okay? Does that make sense?
Mhm.
Who here plays poker?
Nope.
Who here
Blackjack,
plays
not poker.
Huh?
Blackjack, not poker.
Blackjack. Fine, blackjack. How many different two-card combinations could you possibly get in blackjack if you play with a one deck at a time?
4.
4. There's only 4 combinations? What are the 4 possibilities then? Give me an example of 2 cards you can get in blackjack.
Like hearts, right? The
An ace and a 10.
An ace of what and a 10 of what?
An ace of spades and a 10 of spades.
Okay, that's one possibility. Ace of spades, 10 of spades. Give me another one.
Ace of hearts, 10 of hearts.
Another one.
Ace of diamonds, 10 of diamonds.
Another one.
Ace of clubs, 10 of clubs.
Another one.
Everything that adds up to 21.
Oh, wait. When you're playing blackjack, if you get a 21 every time, then you should be in this class. You should go to Vegas and win $1 billion. Okay? I'm talking about what are the possible combinations. You can get a 5 and a 2. A 7
from
and an 8.
all of 52 cards.
Yes, exactly. There's lots of combinations, right?
Yep.
So the question is, how many possible 2-card hands can you possibly get? And the answer is, it's very simple to compute it with the fundamental principle of counting. Just ask yourself the following question. When they give you the first card, how many possibilities are there? If they give you 1 card from a deck, how many possibilities are there?
Is it 1 out of 50?
No, not probability, just how many possible cards might you get on that first card that they give you?
50. Wait, 52, right?
52. You can get any one of the 52 cards, right?
Okay.
Now, next step, they give you the second card. How many possibilities are there?
52.
1.
No,
51.
Can't get the same card twice, right? So by
Yeah.
the fundamental principle of counting, there's 52 times 51 possible 2-card hands. Done. First step, 52 options. Second step, 51 options. Multiply, you're done. That
Can you
is
give another example that doesn't use cards,
sure.
please?
Well,
So I
you know what?
double check that.
You know what? We'll have examples as we continue through the slides. You know, to think of one offhand is I'm drawing a blank. But let's go through the slides and see what kind of questions they have for us. Is that fair?
Mm-hmm.
Okay, so let's keep with the same question. We just flipped 5 coins, or we're about to flip 5 coins. And we know that there's 32 possible outcomes. We just established that. 2 times 2 times 2 times 2 times 2. The question next is, what is the probability of getting all heads in 5 flips? What is the probability of getting all heads in 5 flips?
Does that mean you have a 50% chance of heads in the first flip and then
And the
in
second flip, and the third flip, and the fourth flip, and the fifth flip?
So 16.
16 is the probability? I thought
Well,
probability has to be between 0 and 1.
50% chance you divide 32 by 2.
Well, each flip has a 50% chance heads or tails, right?
Okay.
But you're flipping 5 times. So the question is, what is the probability of getting all heads in 5 flips? So don't think too much. You guys know the answer to this.
So
What is it?
5 out of 5.
100%, 5 out of 5, 100%? You're guaranteed to get 5 heads every time?
Oh, wait.
So Larry?
Is it now there aren't 2 outcomes per event because you're looking for heads? So it's 1 times 1 times 1 times 1 times 1? Or no?
No.
Okay, never
Is
mind.
it 1/2?
It's not 1/2. Remember how we compute probabilities. It's the number of ways of getting what we want divided by the total number of outcomes.
So 0.5 times 0.5.
No.
So
Well,
5 of 32?
Yes, but we're not. So Larry, yes, but we're not doing it that way. Mia, what do you say?
1.5?
Mia, what do you say?
Well, now I don't know if my answer's right.
Just say it anyway.
Well, I said 5 of 32.
It's not. But I just hear what you said. I just was asking. I didn't know if that was right or not. How many ways are there of getting all heads if you flip 5 coins? How many? You can get 5 heads in 5 different ways?
No.
So I'm asking, how many different ways can you get 5 heads? Here, how about this? Let's list them. Ready? Let's list them. Give me a 5 letters, H's and T's, of one possible combination of 5 flips. Go.
H, 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 H.
That's 4. And what's the last one?
H.
Okay, so you can get heads, 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 heads. That's a possible outcome, right?
Yep.
Give me another outcome.
4 H's and a T.
4 H's followed by a tail, correct?
Mm-hmm.
Now, if I were to go through every possibility, and I only listed 2 of them, there's a lot more. How many are there altogether when I flip 5 coins?
1 out of 32.
And again, what?
1 out of 32.
1 out of 32. We already established that there's 32 outcomes.
Oh,
Only one of them gives me all heads.
oh my
One
god.
outcome that gives you 5 heads. Okay. Okay.
Yeah, that's what I'm talking about, right? Yeah, there's 32 outcomes. We already established that in the last step. And
Yep.
only one of them is all heads.
So when will the probability be 0? Because you said it had to be from 0 to 1. When?
Well, probabilities have to be between 0 and 1, but that doesn't mean you're always going to get 0 or 1. It just means you can't be less than 0 or more than 1.
Okay.
But if I said, what's the probability that you roll a die and get a 7, 1 die and get a 7?
1.
No, you can't get a 7. The answer is 0. It's impossible.
Oh, a die?
A die,
Yeah, like a dice.
right? Right, dice is plural, die is singular, right?
Yes.
So if you roll a die, you get a 7, it's 0% chance. It's impossible. You can't get a 7 if you roll a single die. Correct?
Yes.
So that's
Yes.
so that's an example where the probability is 0. But in this case, it's 1 out of 32. Does that make sense?
Yep.
32
Yes.
outcomes, only one of them gives me what I want. 1 out of 32. Now, could I use, this is for you, Talar, can I use an area model for this question?
I don't think so.
Why not?
Um,
And this goes for everyone. Why could you not use an area model for this situation?
It wouldn't be efficient.
yeah, I think the
No.
tree, messy as it is, would be better at mapping it.
Well, there's no question the tree is better, but not because of efficiency. It's because it's not even possible to do the area diagram here. Let's think of what's happening. First choice, that's vertical. Second choice, that's horizontal. The third choice, where's that going to go?
Yeah, what you're
So an
saying.
area model is only good when you have like
2.
things.
2.
Wait,
An
what's
area
the
model
third-
is only good when there's first flip, second flip. First this, second this. First choice, second choice. Now, if you can somehow create a 3-dimensional picture,
Then it may
then you
be
can know
easier.
3 choices. But why would you want to, first of all? And even if you could, you can't do 5 choices like we have here. But a tree diagram can go on forever. Right, a tree
Yeah.
diagram, you have your first, right, tree diagram, right? So first choice, second choice, third choice, fourth choice, and so on, right? You can, depending on how much space you have and how much room you're willing to write and how small and neat, you can go on forever, but you cannot do that for a tree diagram. Does that make sense?
Yeah.
Okay, so could an area model be used? No. Could a tree diagram be used? Yes. That answers that question. Okay, so this is it for the fundamental principle of counting. That concept is now over. We are now moving to the next concept in counting, which is the idea of permutations.
Oh boy.
You don't even know what a permutation is.
Can I ask a
Don't
question?
all boy till
already.
you know it. You can't all boy till you understand it. Then you can, or not understand it. Then you're like, oh boy, like I can do it. You can't do it. That's not fair. Mia, you have a question?
Yeah. So I just wanted to clarify that with this like last problem and all of the other ones to come, the 32 is just like the probability. So always calculating the probability, it would be multiplying like all of the outcomes together. So like writing out, like if we were to write out every possibility of like the heads and the tails, it would come out to be 32.
It would be 32 possibilities, correct.
Okay. Thank you, sorry.
So if I said, what's the probability of getting 4 heads or more, it would still be over 32 because there's still 32 outcomes, but now it's more than one way of getting it.
Got it.
So your numerator would be different. Okay, so now we're moving on to permutations. And to illustrate permutations, let's look at this children's toy. Is everyone familiar with this children's toy?
Yes.
Yeah, the little rings.
Yeah, I don't have mine anymore. I threw it out last week, but you know, it's very exciting. It's 6 rings of different colors, and the idea is for the child to put them on the post, largest to smallest, right? That is the goal. And some children are very slow and they don't really do it right, and they just kind of put the rings on randomly. And the question that we're going to ask each other is the following: how many different ways could the child select the first ring to put on the post? Which means the rings are on the floor, the post is in front of the kid grabs a ring and puts it on. How many different ways can the kid do that? How many different rings are there possible for the first post? Or for the first
6.
6, right? It could be any one of the 6 rings, correct?
Yep.
Okay, now, once the kid has put, or adult, depending on who's playing, has put the first ring on, how many choices do we have now for the second one?
5.
5.
5. How about the third?
4.
4.
Fourth?
3.
3.
Fifth?
2.
2.
Sixth?
1.
1.
So by the fundamental principle of counting, how many different possible ways are there for the kid to put the rings on the post?
So 5 times 4 times 3, so on and so forth.
Well, it is so on and so forth.
720?
Well, what's the first number?
6.
6,
Times
5,
5.
right? 6 times 5 times 4 times 3 times 2 times 1.
720?
720. So there's 720 ways for the kid to put them on correctly.
Okay.
So when it says, what rule did you use to compute this? This is obviously the fundamental principle of counting. Correct?
Mm-hmm.
Now, what is the probability that the rings are going to be put on in the right order?
1.
100%? 1?
No.
1.
1 out of 720.
1 out of 720. 1 over 720. 720
Oh.
possible outcomes, one of which is the correct order. So 1 over 720. Which means if the kid proudly shows you the post and they're on in the correct order, would you say, yeah, you just got lucky? Or would you say, oh, the kid has a deeper understanding of spatial reasoning than I would expect for a 7-year-old? That type of thing. Okay, so if it's 1 in 720, that's pretty unlikely to occur randomly. Right, 1 in 720 is pretty rare. So if it happened, I'd say, okay, you're smarter than I thought. Maybe you're not that dumb. Thanks, Mom. Okay, anyways, now, so far we haven't gotten to the permutations yet. So far, all we've worked on so far is the fundamental principle of counting. So now we're going to develop the idea of permutations. And the question is, how many ways are there to put on just the first 2 rings?
6 times 5?
Excellent, 6 times 5. First ring 6, second ring 5, 6 times 5.
30.
Right, there's 30 ways to put on just the first 2 rings, correct?
Mm-hmm.
How many ways are there to, I want to write this stuff down, hold on. So all 6, it was 6 times 5 times 4 times 3 times 2 times 1.
Mm-hmm.
The first 2 was 6 times 5, and the first 3 is how much?
6 times 5 times 4.
6 times 5 times 4. And I really don't even care what that number is. I mean, it's not hard to calculate, 120. but it's the approach that matters. 6 times 5 times 4, whatever that number is. Okay? So the question now is the following. All of these examples are when you have a total of 6 objects, correct?
Mm-hmm.
All these examples are 6 objects. If I have, let's say, 17 objects, and I want to pick the first, let's say, 5, then how many ways are there of picking 5 objects from 17?
Is it 1 times 2
One
times?
second, follow the pattern. The first choice, how many possibilities are there?
17.
Oh, 17.
17. Second choice, how many possibilities?
16.
Third choice.
15.
Fourth choice.
14.
Fifth choice.
13.
Right? And you're picking 5. So this will be whatever number this is your answer, correct?
Mm-hmm.
So what we want to do is we want to come up with a formula that works and that includes all of these 4 cases. And who's there? Who is that? Are you ready to learn some math? Yes. You want to learn some math? Yeah, go. Oh, the kid's like disappearing. It's like a disappearing trick. That's kind of cool, actually. You should go to Vegas with that. Anyway, so we want to come up with a formula that'll work for all of these cases. And the formula is as follows. First of all, we have to define something. So I'm going to erase this. Can I erase all this? You have it all written down, hopefully?
Mm-hmm.
All right.
Professor, are we still in slide 6?
We're on the slide with the permutation box, but I haven't gotten to that box yet.
It's
Oh,
like
okay.
Okay, I haven't
Okay,
quite
thank
gotten
you.
to that box yet.
We're almost at slide 7.
Huh?
We're about to get to slide 7.
About to get to slide 7. Okay. So first what I'm going to do is I'm going to define something which you may have seen, maybe not. What is this symbol?
I forgot what it's called.
Well, called an exclamation. Come on. You know anything about English?
Exclamation point.
Well, if this was an English class, it would be an exclamation point.
Oh, it's factorial or something.
It's called a factorial.
Factorial.
For factorial. 1 factorial is equal to 1. 2 factorial is equal to 2. 3 factorial is equal to 6. Now, for those of you who have never seen this before, do you see the pattern yet? See, if I didn't have this, you might say, oh, it's easy. It's just 1, 2, 3, 4. But once this one comes in, now all of a sudden that kind of throws it out the window.
Oh, you're multiplying.
So do you, yeah, say what?
Multiplying. The equals 1 times 2, and then 2 times 3.
So
And
what's
then 4
4 factorial then?
Yeah, 24.
24. 5 factorial.
24 times 5.
20. 6 factorial.
120 times.
720.
720, and so on. What factorial means for whole numbers, like it is here, you take that number and multiply down to 1. If it's already 1, of course, it's just 1. 2, down to 1. 3, down to 1. 4, down to 1, and so on. Okay? This is the idea of factorial. It is simply a shorthand notation to make it easy for us to write formulas down. Okay? Now, there is one special case which you should know, and that is 0 factorial. Anyone know what 0 factorial is?
0.
It is not 0.
Is it
1?
undefined?
It is 1.
Oh, I got it right.
Hey, even a stop clock
That
is
was-
right today, huh?
That was a total guess.
You know, sometimes guesses have deeper intuition behind them than you even realize. It's kind of like dreams are supposed to be very prophetic, right? And sometimes they're just a complete other coincidence. So there's always the possibility. Yes, Tolaire.
Why is it 1?
It's a great question. The reason why it's 1 is because formulas that we use for other cases would also work for that case if it's equal to 1. So we just say it's equal to 1. We just say, you know what, all these formulas are going to work amazingly if it's equal to 1. So you know what, just say it's equal to 1. Right? Are you a religious person, Solaire?
Sure. No, not really. I don't know.
Not really. Okay. Well, I'm semi-religious, or at least I was growing up, and I've read the Bible many times, and I have never seen factorials in the Bible ever. Right? And God said, let 6 factorial be equal to 620 or 720. That never happened, right? Right? It never happened. So mathematical constructs, even though, you know, we believe, at least I believe, that everything comes from, you know, a superpower, a higher power. These are all created by man and women, right? Mankind, womankind, humankind, whatever you want to call it. And we get to define things any way we want as long as they're useful to define them that way. It is useful to define 0 factorial to be equal to 1 because other situations are then nicer.
Okay.
That's the reason. That's the only reason. Okay? It makes other formulas easier. That's all I can say. Okay. So now let's get back to that question that we had, which is as follows. You have 17 objects, and you pick 5 of them. How many different ways are there? How many ways are there of picking 5 objects from 17? First object, how many ways?
17.
17. Second object, how many ways?
16,
16. Third object?
15,
Fourth object?
14,
And fifth object.
13.
So whatever this number is our answer. But now I'm going to do something that seems very strange. I'm going to multiply this by 12 down to 1, and I'm going to divide by 12 down to 1. Before I explain why am I doing that, what's the word next to 17? Objects, 17 objects. Okay, before I explain why I'm doing it, first let's make sure that I am allowed to do it. Can you multiply? I don't know how to, can I spotlight my video? There you go. Can you multiply and divide by the same thing without changing the value? If I have some number, can I multiply and divide by the same thing without changing its value? Sure. 5 over 5 is just 1. You're multiplying by 1. Right?
Yeah.
So, by putting that in here, I haven't changed its value. It's still equal to the same thing. The question is, why would I do that? Because now, let's look at the numerator. That's my new numerator. Can I write that in a nice, succinct way?
Can't you just write 17 factorial?
Yes, I can. And here's my denominator. Can I write that in a nice, succinct way?
12 factorial?
12 factorial.
So the number of ways of picking 5 objects from 17 objects is 17 factorial over 12 factorial. In general, if instead of having 17 objects, I say I have n objects, and instead of 5, I have r, so I use the letters n and r instead of 17 and 5, then what would my answer be? What would I put on top?
N factorial.
N factorial. And what would I put on bottom? R is 5. I don't have a 5 here. All right, so it's not n factorial over r factorial.
12 no.
N minus R
Uh,
factorial.
N minus r factorial. And that is the formula on the top of page of slide 7. The formula on the top of slide 7, let's look at it. First, there are n factorial ways to line up n objects. But if you only want to line up r of those n objects, then you only use the first r factors. So there's n factorial over n minus r factorial ways to do this. So what they just summed up in 3 lines with no preliminaries, I just spent 10 minutes establishing. Okay, but that is the formula. So let's look at the next question after that. How many ways can 5 teachers be assigned to 5 classrooms? So suppose you're in a new school, they just built it, and there's 5 classrooms, and you and 4 other teachers come in and you say, oh, we all get our own classroom, this is so exciting. How many ways can the teachers be assigned to the 5 classrooms? So let's think about it. The first teacher, how many different classrooms can the first teacher go to? 5. Once that teacher has chosen a classroom, and it's the next teacher's turn, how many ways can that teacher choose?
4,
And then?
3,
And then?
2.
So overall, how many ways can 5 teachers be assigned to 5 classrooms?
5 times 4 times 3 times 2 times 1.
Which is 5 factorial, which becomes?
80.
No,
One
not
time.
80. What's
120.
120. 120. Right? 120.
Yeah.
Okay, now next question, a little more challenging. It says 5 teachers are to be assigned to classrooms, but only 3 classrooms are available, so 2 teachers will have to wait. How many ways can the assignment to available classrooms be done?
Is that 5 times 4 times 3?
Excellent. First teacher, 5 possibilities. Second, 4 possibilities. Third, 3, 5, 4, 3, right?
Mhm.
So 5 times 4 times 3, there's 60 ways of doing that. Does that make sense?
Can you explain that
Sure.
by doing it in the formula?
Yeah. So in this case, there are 5 teachers, right? There's 5 teachers, but how many of them get a classroom?
3.
3. So we're picking 3 of those 5 teachers. How many ways can we pick 3 of 5? Well, according to the formula, it's going to be 5 factorial, that's my n, over what factorial?
5
5
minus
minus 3.
Or 2 factorial.
Yeah.
Which is 120 over 2. So there's 60 ways of doing that, which is exactly what we got by doing 5 times 4 times 3. Make sense?
Mm-hmm.
Yeah.
Okay. Now, next question, a little more challenging. 5 teachers are to be assigned to 7 classrooms, so that 2 classrooms are going to be left over. How many ways can this be done? I want you to take a minute and think about that.
Could you repeat the question one more time?
Well, it's on the PDF. 5 teachers are to be assigned to 7 classrooms, so 2 classrooms are going to be left over. And the question is, how many ways can this be done?
Would our numerator still be 5 teachers?
Well, that's for you to figure out. Part of the reason that the mathematics of counting can be very complicated is because it's not always obvious how to arrange the objects in a format that makes sense. How many things are you picking here out of how many things?
We're picking 5 out of we're picking 5 out of 5.
I'm sorry, say that again?
Are we picking 5 out of 5?
Well, then you're not taking into account 7 classrooms, are you?
It's picking 5 out of 7.
You're picking 5 out of 7. You're picking the classrooms here, not the teachers. Right? It's the classrooms now that you're picking. There's 7 classrooms and you're picking 5 of them.
What you are picking makes a difference. Like
Yes, 100% it does.
Right.
100% it does, yes.
Okay.
So you're picking the classrooms here. Right? You're not picking here the teachers anymore. Every teacher is going to get a room. You're not choosing which teachers you're going to pick. You're choosing which classrooms you're going to pick. Right? There's 7 classrooms, you're picking 5 of them.
I just think we're having a hard time because there's no visual. Like, see, like what you're explaining, you're not annotating or writing on the board, so I think it's hard for us to follow.
Well, that's fair. I'm not sure what I would write in this case, though.
I mean, just in general, you're not doing that. So like me personally, I feel like I'm not following because there's no visual to go along with it other than the PDF.
All right. Well, I will try to, what can I do about that? I'll try to figure out something I can do about that. Figure out a better way of doing this that makes more people happy. But nevertheless, this particular question for now still remains, which is there are 7 classrooms, and we're going to assign 5 teachers to the 7 classrooms, correct? Let's see, can I share a screen and annotate? Let's see how I can do this. So can you all see this?
Yes.
Yeah.
So let's see.
You go to view options for annotating next to your sharing screen.
Where am I looking? More?
Go up here where your mouse is, go a little bit up, view options.
I don't see anything that says view options.
Oh, it should have popped up. It's like next to the green portion that says that you're now sharing.
Interesting. I don't see that. But
If you hover over the screen that's being shared and you move your mouse up, you should see a green that says you are sharing.
yeah, you don't see me. You don't see this part. You were.
We don't see that. No, we don't see that. But right next to it, there should be a view options or some drop down you can click, and there should be an annotate.
Oh, I already have annotate. I thought you were giving me something else to do. No, I already have annotate. I thought you were.
That's what it is. Yeah.
Yeah, I already have annotate here. So
Yeah, just that.
in this case, there are 7 classrooms, right?
Mm-hmm.
Of those 7 rooms, how many are you taking?
5.
5. You're not picking teachers here because every teacher gets a classroom. You're picking 5 rooms out of the 7 rooms. Here, there were 5 teachers. This is horrible. How does anyone do this?
You can use a text box if you see the T with the when you annotate. Never mind.
What I see a T, I see text.
Oh. Okay, so you can put it, yeah, and now you can type.
Oh, crazy. How come no one told me about that? Oh my God. Okay. That makes it so much easier. So right here, text. So here, there were 5 classrooms, and we pick 3 classrooms.
Mm-hmm.
Sorry. Yeah, no, sorry. I was in the wrong one. Here there's 5 teachers. Right, here's 5 teachers, and we pick 3 teachers. right? We're picking the teachers. We're not picking the classrooms here. We're picking the teachers. Here, on the other hand, in this case, there are 7 classrooms, and we're picking 5 classrooms. So what you're picking makes a difference. Right here in this example, of course, it was 5.
Wait, for the last one, sorry, just so people don't get confused, there's 7 classrooms, but there's 5 teachers that you're picking, correct?
But that's not the point. It's not the 5 teachers. The 5 teachers are being assigned to 5 classrooms. You are picking, you're not picking teachers here. All teachers get a classroom.
Okay.
You are picking the classrooms.
Okay.
How do you, oh, I can't, can I,
Okay, wait.
how do I,
If you want to move your whole screen, then you have to erase what you've already written, sadly.
that's horrible.
I know.
But I don't want to erase everything. I just want to erase this part.
Oh.
Oh, here, I'll just do this. Hold on. I'll make do.
Yeah, that was my mistake.
We are picking in this case, we are picking 5 classrooms.
Mhm.
We're not picking the teachers here. Every teacher gets a classroom. We're picking the classrooms. In this case, we're picking the teachers. Right? 5 teachers are to be assigned, but only 3 of them are going to be picked. Here, every teacher gets a room. There's 7 classrooms, but we're only going to pick 5 of the classrooms. So it's very important when you read the question to know what the objects are that you're choosing from and what the objects are that you're picking. Does that make sense?
Mhm.
So if I scroll down now, okay, this is a good place to stop because the next idea is combinations, and I do not want to go to combinations today. So this will be the end of, we did the fundamental principle of counting and permutations today. You can start your chapter 3 homework. You shouldn't be able to answer everything yet because we haven't finished it, but you can certainly answer the stuff involving the fundamental principle of counting and permutations. And we'll have a quiz next time on chapter 2. The solutions are up, and you can look at the solutions to your questions. And this time I might not pick one of them. This time I might pick a completely different question that's related to the original questions. But if you know how to answer your homework questions, you should have no problem answering this question. I haven't decided yet, but I might, because on the quiz, there were people who magically got part C correct, but had a wrong A and B. And you can only get part C if you do A and B correctly. Which leads me to guess either that some people were just not being very honest, or benefit of the doubt, they didn't remember A and B, but they remembered C. They just remember what the answer was, which is certainly possible. But I might just do a new quiz so that it removes this temptation. So we'll see on Wednesday. Okay?
Professor, are we going to go over the question that we were doing next time?
The question that you were doing.
The one that we were just doing right now.
The one on the board?
No, the one that everybody was stuck on.
Teachers.
Are we going to review it
The
next time?
7 classrooms problem.
Oh yeah, the one that we just did. Yeah, we can start
Okay.
there. Yeah, we can review it. It's not a problem. I would recommend trying to figure it out before class. But yeah, we can certainly start there and then go on from that point. I have no problem with that.
All right.
Just remind me in case I forget.
Thank you.
Thanks,
Okay.
Professor.
All right, guys. I will see you guys on Wednesday.
Professor.
Thank you, Professor.
You're welcome.
Sorry, my audio was cutting out. So for our quiz on Wednesday, it's only on chapter 2 or the second PowerPoint.
Only on chapter 2, correct.
Okay. All right.
No problem. You're welcome.
I had a question, Professor.
Yeah, go ahead.
For going back to the tree diagram,
Yeah.
based on the PowerPoint, I know there's, it has the little squares labeled, but the very first square at the beginning that's blank, is that just
That's just your starting point. There's nothing there.
Oh, so we don't have to fill that one out or anything?
Nothing goes there. It's the first column, the branches that leads to your first decision. The first,
okay.
The first one is nothing.
Okay, cool. All right, that was all.
Okay, no problem.
All right, cool. Thank you.
You got it. And then there were two. I still can't hear you. Can you hear me? You can hear me. I can't read lips, unfortunately. I'm gonna stop recording for